Oh, all right. Now, just to finish off today, you may be aware that there was quite a ferocious solar storm a few days ago, but it didn't produce many aurorae. And lots of people have been scratching their heads saying, well, the strength of that storm, the strength of that mass ejection from the sun, it should have produced really strong aurorae, but it didn't. So Daz is now going to tell us why exactly that didn't happen. Aren't you, Daz?
Well, I'm going to try and explain it. It was a bit of well, it was a disappointment for a lot of people. There was some aurora, but nothing like we were expecting. I mean, first of all, we saw. Oh, hang about. Sorry, I've got the wrong one. There was a. Let me just flick through these, because I've got to get to the alert. What we saw on Saturday, we all knew this was coming. What we saw on Saturday, just before, between 3 and 4 o'clock, we got, well, even about sort of like just before that, you saw an amber alert arrive, and then all of a sudden the bars shot up, and of course we were expecting a very big storm that was going to last possibly for nearly 24 hours. But as you can see, it started at 1600, but between 3 and 4 o'clock, so it was still daylight. So that was a bit of a disappointment. And what happened was we could see it grew, then it dropped down again. Oh no! Then it grew again, but by this time, we were getting in towards the twilight and the dark hours. Now the thing is that because we knew this was coming. This was from an event that had happened on the sun about 3-4 days before. And what we need to actually look at is what we... so I've got to go back, so I got these in the wrong order. So when we talk about the sun, what are we actually looking at? If you've got a quiet sun, what you normally get is just a solar wind. Or you may get high-speed streamers and interplanetary shock waves from small events that happen on the sun. So these will keep us bathed in the solar winds normally during the normal times and all that, but we won't be seeing anything spectacular happening. Then we get an active sun. Now, when you get an active sun, we're looking for solar flares. And these release X-rays and radio bursts traveling at the speed of light. So, like we were talking in my previous talks about the sun, the Carrington event, Mr. Carrington and Mr. Hodgson were both viewing the sun at the time, and they saw a massive white light. And that was the solar flare that had happened 8.5 minutes earlier. So, traveling at the speed of light, it had taken 8.5 minutes to arrive here. Well, of course, at the time, he didn't, assume that there was anything special, but he did record it, and he'd made some drawings. Now, included in this, you get SEPs, which are solar energetic particles, which is the radiation, basically, which is mainly protons and electrons traveling just under the speed of light. So if you get a flare, usually you'll see the flare. If it's a white flare, it has to be a big X-class flare. Then what you will see is the sunspot area where it's coming from will suddenly brighten, and then about so that'll be the actual first light arriving, and you will see a ray in the magnetometers on the Earth. You will see a blip in the actual trace, and that'll be the main crochet. And then usually about half an hour later, you will get the main storm come in behind. Now, this will give us aurora, but things have to be right, and I'll get onto that a little way better. But even better, if it's associated with a coronal mass ejection, a CME. And this is where massive amounts of solar plasma and enhanced magnetic fields actually break away and erupt out into the interplanetary media. Once it's out in the interplanetary media, it becomes an ICME, which is interplanetary coronal mass ejection. And this is the actual storm that will be moving towards us. and it'll drive strong shock waves out into space. Usually they're slow moving, about 1,500 kilometers a second. Yeah, that's slow, isn't it? But they'll take about 3, 4, maybe 5 days to actually arrive at Earth. It says here 2 to 5 days. But if they're also associated, and they cause the geometric storms on Earth, but if there is also a coronal hole actually on the planet, on the sun, sorry, at the time as well, and that is Earth facing, you will get a combination of all these things, because when you get coronal holes, you get enhanced solar winds. Now, this is, as you can see a coronal hole here in the bottom left. And what this is all the orange area. That is where there is high magnetic action going on. So it's producing, we can actually see it. But what happens is this black area, which is the actual hole, isn't actually a hole itself. It's just where the area is a lot cooler. There's very, very little magnetic action going on there. So the radiation or the photons and all that can actually escape, because what's happening is where there's magnetic action going on, the material, the photons and everything else, the heat, all the radiation particles and everything are being held into the next to the sun, just above the chromosphere. So they're heating it up. But where there is no magnetic action going on, it's cooler. It's like a big, massive sunspot, really, except it's not something that's broken through the surface. It's the same sort of thing. It's cooler. That's why it's black. Now, that will give us enhanced solar wind. And this will also give us, maybe if it gets really heavy, you can have a very small aurora, but it'll be right at the poles if it gets really enhanced. Well, the combination we had, and of course, as it comes out, you will see on the bottom right, this is the solar radiation that has come from a coronal mass ejection and a solar flare. And as you can see, all this snowiness on the solar radiation image is actually the radiation hitting the sensors on one of these satellites, one of the coronaspheres on the satellite. So this is what we've been expecting. We expected it. Now, of course, we're protected by Earth's magnetic field. The image on the left is wrong. The magnetic field does not emanate from the poles and then go around and to the other pole and all that. The image on the right is how the magnetic fields on the Earth are actually aligned. They come out all the way down, and you can see they actually emerge, some of them just around the equator, and then they just pop over and that. But you can also see the magnetic field is going south to north. And I think that's quite important, that's south to north. And you'll probably right, so this is what happens when you have a coronal mass ejection or a solar storm coming towards you. You can see the storm just leaving the sun. The shock waves coming towards the Earth, which is on the right hand side, and you can see the Earth's magnetic field defending us. You can see these magnetic field lines actually peeling back and they will flow behind us. They don't actually break away from the actual Earth itself, and they will form a massive teardrop shape, and they will be not only guiding radiation away from us, around the back of us, but also they'll be drawing some of that radiation back into the poles, and that will give us our enhanced aurora. So this is what we were hoping for. We were going to see some lovely aurora throughout the whole of the UK. But as we know, it didn't happen. So what I've got to quickly talk about is the structure of an ICME. So what you've got, I've got numbers on the top. At the top, you can see the sun. Now you can actually see on the right hand side, basically the black line that is in front of just the Earth, that is the shock wave. Now this will drive radiation towards us. Then what you've got, if you come back towards the sun, you can see these red lines that are actually coming round to Earth, and this is magnetic lines which are in the moving along into the back towards the sun. But this is all full of radiation as well. But what we're looking at is this coiled and this orange bit here. This is the core of the actual solar storm, and it's called a magnetic rope. And this coil is what we need to be looking at, and what's actually inside this. As I've said before, this has a magnetic structure within inside it, and what the actual layout of this magnetic structure is will dictate on whether or not what sort of storm we're actually going to have. So next on, so there we go. So what I'm going to do is I'm going to stop this. Now I've got a prop here, this very, very expensive piece of equipment. And what I'm going to have to do is I'm going to have to take off my my background, because so we can see it. But this was very, very expensive. I had to go and buy this special. And so here we are. Excuse the mess behind me. So
we had to club together for this, didn't we, Dad?
Well, I'm going to put a chit in. I want the money back.
Okay.
And here it is. It's a slinky. Okay. So now, when I was talking about the flux rope, or the core of the actual storm, this is the actual shape of it. It's a tunnel, just like that. So you can see all the way through it. Now, what this is it actually leaves the sun, and it forms a bow wave, which comes towards us. And as I said, if this is being driven by, it's like that. It's that shape. So you've got the loop there. So what you've got is this this slinky, as we call it. And what's happening is within this, it is actually full of magnetic waves, magnetic fields. Now, there are several ways that this actually works. And what happens is, as it comes out from the sun, it spreads out and it gets bigger. So what's happening is these legs are still attached to the sun. And what you've got is you've got magnetic fields running around this actual slinky, as it is here. And what it is, because it's round, this is going actually around the slinky like that. Okay, so it's all right. It's getting away from me. So what you've got is you've got the magnetic fields going around that way. So, or they could be going this way. This is what I mean. I think there's about 8 configurations of what you can have on here. So if it's going this way, for argument's sake, it's going south at the front. So it's coming down, and then it's coming around and up at the back. So you've got south, as you go through, as it passes through the earth, when you come out the back, it will be going north. Right through the middle, again, you've got magnetic fields all the way through this. Right through the middle is what you call the axial magnetic field. And this will give you your east and west field. Now, what this will do, depending upon which way it's facing, it's either going to be westwards or it's going to be eastwards. If you can see that. So if you put the pen through, if you can see the silver tip, it's that's east, or that'll be west. So what you've got is south, east, west. Okay, and that's the actual structure of this magnetic flux rope. Now, trapped inside here is lots of radiation and energetic particles. They're encased in it. It's like a prison cell, and they're all whizzing around. They're going up and down these magnetic fields, and it's how this actually hits us depends on whether or not we get good aurora. Now, what happened the other day, because you've got, what you need is you've got to have a south field rotation on this as it stands there. Now, they can either hit us like that, or they can hit us like that. Okay, so but you've got to have that south facing rotation of the actual magnetic field, so the particles are going, and it's those that actually that's what actually causes aurora on the earth. And but you've got to have that south facing facing. So if it comes at us like that, somewhere along there, you're going to have a south facing magnetic field, which will then give us a massive aurora. And depending upon how much radiation or SEPs is actually involved in this, which will then flow back into the poles through the Earth's magnetic field lines, that dictates how much aurora we get. But if it comes to us like this, there are two ways. I mean, of course, like I said, the rotation of the magnetic fields can be either way. So you can either have west, south, west, east, or east, south, west. So it doesn't matter as long as you've got a south component. But it came at us like this, in that direction. And what we were hoping is that it twisted so that we would somewhere along the line get the south concept. But what happened is this was going east, the front was going east, the back was going west, but the actual field in the center was going north. So of course that means we had no south component to actually help the aurora to actually happen. So this is why we didn't get the aurora we were hoping for. We had no south component. If it had been like that, with it being east, south, west, we would have had a beautiful aurora, and we would have seen it all the way probably down to the south coast of the UK and possibly beyond. But that is what the problem was. We had no south component of the magnetic field within the magnetic flux rope that actually came from the sun. So yes, we got all the radiation, we passed through the radiation, we had all the magnetism, but unfortunately it didn't produce the aurora because we didn't have the south facing magnetic field. And I hope that makes a bit of sense. It's a lot more involved than that, but that's what it was. We didn't have a south facing actual magnetic field, and that's what would have opened up our atmosphere to the aurora, which would have come down and gone down to low latitudes. So I hope that explains a bit why we didn't get the aurora that we were all hoping for. So I'll leave it there because it can get quite complicated. I'm sorry.
No, thank you very much, Des. I mean, for those people who might have thought that if you do get a big solar storm, it automatically means an aurora, it obviously doesn't.
Yeah.
So,
as I said before, we cannot predict what auroras are going to do because every single one is different.
It's different. Yeah. Fascinating stuff. Right. And good to see you get your slinky out, Daz. So
yeah. I'm sorry, I'll be sending a chit in. I mean, this was very, very expensive. It's an expensive bit of equipment. It's got dinosaurs on. I did show you earlier. No, it's. I'll be playing with that later on the stairs.
Obviously meant for you, Daz. So there we are. And I like the way you're handling your slinky there. Perhaps you ought to take up the accordion.
Well, I lost control of it a couple of times, so it's maybe I shouldn't.
Yeah. All right then. So I think we'll start drawing things to a close for this evening. I'd like to thank Dave Saras for being with us this evening and talking about the